This topic is the second part of the fundamental theorem of calculus, part 2. It is based on a function f being continuous. It is about what's called a function defined by an integral, and it is exactly what it sounds like. I have a function here that I'm calling g of x, and it's defined as being the integral of another function that I'm calling f of x. The key to this is seeing that my independent variable, this x, appears as a limit of integration. It appears as my upper limit. So when I go to evaluate a function like this and I want to substitute a value in and say, find, for example, g of 2, where I'm going to plug that 2 in is this upper limit, and then I'm going to take an area approach to evaluate that integral. Before we talk about what this part of the theorem actually says, I want to look at what happens when I take the derivative of this type of a function. In working these 3 examples down here, you'll get an idea of what the second part of this fundamental theorem of calculus says. So in each of these, I'm given a function g of x. In this first one, it's defined as the integral from pi over 2 to 2x of cosine t dt, and I'm asked to find its derivative. The first thing that I'm going to do is just focus on this integral part. I'm going to go ahead and just evaluate that integral using the first part of the fundamental theorem, which says, let's find the antiderivative first. The antiderivative of cosine t is sine t. My limits shift to the end, and now I'm ready to substitute the limits. Upper goes in first for that t. Then I subtract what I get when I plug the lower limit in for the t. Doing that gives me sine of 2x minus sine of pi over 2. Now I'm going to evaluate the sine of pi over 2, which is 1. And that gives me g of x equals sine of 2x minus 1. The question originally wanted me to find g prime of x. Now that I have g of x in this form, I'm going to go ahead and find the derivative of it. Term by term, when I do the derivative of sine 2x, I'm going to have to use the chain rule. And here it is. The derivative of sine of 2x, I do the derivative of the outside. Derivative of sine x is cosine. Leave the inside part alone, so that 2x this comes down, times, and here's the chain rule part, the derivative of the inside, which is a 2. My minus 1 here, because it's a constant, just drops off. And what I have sitting here is g prime of x. All right, so that was fun. Let's go ahead and do another one. In this one, I'm going to do it the same way. Let's first find what g of x is. I'm going to go ahead and evaluate this integral using the fundamental theorem, part 1. Which is, let's first find our antiderivative of 2t plus 5. Here is my antiderivative, t squared plus 5t. I'm now ready to take my upper limit of 3x and plug it in for my t's. And now I have this as my g of x expression. I'm going to go ahead and simplify what's in the parentheses a little bit. So here is my g of x, and all I've done is I've evaluated that integral. This question wanted me to find g prime, and I'm now ready to find g prime. Using my power rule for derivatives, I bring down the power and subtract them from the power. Gives me g prime of x equals 18x plus 15. I spot a common factor of 3 that I'm going to factor out. Here is my final g prime of x expression. Let's take a look at one more example, and I think you'll see what's going on here. In this one, my integrand is actually a little bit more abstract. I don't have an actual expression right here. I'm just calling it f prime of t dt. But the question is still the same. F prime of t is the derivative of what? And the answer to that is simply f of t. The limits shift to the end. My next move is to take each one of these and substitute them in for the t. That gives me a g of x of f of x squared minus f of negative 8. Because I am being asked to find g prime of x, I'm now going to take the derivative. And you remember from when we talked about the chain rule that this x squared is an inside function. This first part needs a chain rule. I'm going to do the derivative of the outside function. That's going to be f prime. I leave the inside part the same, so that x squared just carries down. And then I multiply times the derivative of that inside part, which is a 2x. For the derivative of this f of negative 8, I don't know its actual value, but I do know it's a constant, because when I plug it into whatever f is, I'm going to get a number. Its derivative is just going to be 0. And I end up with the g prime of x of f prime x squared times 2x. Let's take a look at a summary of these three examples and see if we can spot a pattern that's going on. So for this first one, notice my integrand was a cosine, and this is a cosine. That 2x that is part of that derivative answer is simply my upper limit. What has happened is that upper limit was plugged in for the t. This 2 showed up by taking the derivative of that upper limit. Derivative of 2x is just 2. That pattern is going to hold in the next one as well. So let's take a look at this one. My upper limit of 3x was plugged into that t. When it was multiplied by the 2, that's why it's appearing here as a 6x. The plus 5 is just part of that integrand. The 3 here came about by doing the derivative of that upper limit. Derivative of 3x is just 3. And that same pattern is going to hold for number 3 as well. If I take that upper limit of x squared and plug it in for the t, that's going to give me f prime of x squared. Multiplied by the derivative of that x squared gives me this multiplied by 2x at the end. And this shortcut you see going on is what we call the fundamental theorem of calculus part 2. It says that if you have a continuous function, f, on some closed interval ab, and u is a function of f, notice that u is my upper limit. This lower limit is a constant, so a is that beginning interval. And if you want to find the derivative of this function that's defined as an interval, all you really have to do, instead of doing all this work that I had done up here, which was to evaluate the integral just to turn around and do the derivative, all you really have to do is take that upper limit, that function, and substitute it into your f function, your integrand, that's this f of u, and then multiply times its derivative. So it just saves you a lot of work. You don't have to go through finding the antiderivative just to turn around and find the derivative. And if you think about why this is working, it makes perfect sense. It's because integrating and differentiating are inverse operations, so they undo each other. So these two operations have the same relationship as adding and subtracting, multiplying and dividing, square rooting and squaring. So if I'm going to do an antiderivative of f just to turn around and do the derivative, I'm just going to end up right back where I started. Just to offer you a simple example, so say you had 59, and I said, all right, so we're going to start at 59, let's add 28, and then subtract 28. So there's two ways to do this. You could start at 59, you could add the 28, get that answer, subtract the 28, and come up with your answer of 59. Or you could just recognize that these are just undoing each other. So you could just say, well, if I start at 59 and I add 28 and subtract 28, I'm going to end up right back at my 59. It's the same thing that's going on here. I'm starting with my f of t. If I'm going to do an antiderivative, just to turn around and then do a derivative, I'm going to end up right where I started. Let's take a look at a few examples and you'll see how this works. So on this first one, I have a function f of x that's defined as an integral, and I'm asked to find the derivative of f. I see my lower limit is a constant and my upper limit is a function of x. And what this theorem says is all I have to do is take that x and plug it in for my variable, and then multiply times its derivative, which is just 1. So this is my f prime of x. If I would have done this the long way, I would have had to find the antiderivative, evaluate it along these limits, and then find the derivative, but this is exactly where you're going to end up. Another example with the same idea, I have y, which is defined as an integral, and here I am asked to find the derivative of y with respect to x. I have a lower limit that is a constant. My upper limit is a function of x. What the fundamental theorem says is all I have to do is take that upper limit and plug it into the variable in the integrand, which is this t, and then multiply times the derivative of the upper limit, which is times the 2x. And that is it. So if I were to find the antiderivative and turn around and find the derivative, this is what I would end up with. The beauty of this is I really don't even know how to find this antiderivative of sine square root of t. That's something we haven't learned how to do, yet we can go ahead and answer this problem and come up with the answer. we could simplify this a little bit. So where you have the square root of x squared, you could just call that x. And that will give me my simplified answer. Let's look at how we can apply this to some graph analysis questions here. In question 3 down here, it says that f is defined as the integral from 0 to x of g of t dt. And what I'm looking at over here is the graph of g. In this first question, it says to find f of 2. So that means that my x is 2, and x is the upper limit. So make sure in doing this, you replace the correct variable with the 2. Since x is the independent variable and x is that upper limit, the 2 goes here as my upper limit. From here, I take an area approach to evaluate this integral. This says, let's look at the graph of g, and this is the graph of g, from x equals 0 to x equals 2, so I block off the interval. So from 0 to 2, and I find the area between g and the x-axis, which is the semicircle right here. So I'm just finding the area of the semicircle. Looks like I have a radius of 1. The pi r squared is the area of the circle. I divide it by 2 because I just have a half a circle, and that gives me a final answer of pi over 2. Moving on to the next question. Now this one's f prime of -3, which means I have to refer to my function f of here, which is that integral, and find its derivative, and this is where that fundamental theorem comes in. What it says is, if I do the derivative of a function defined as an integral, all I do is take the upper limit and plug it in. And that establishes a really important connection, and that is that f prime equals g of x. So when this is asking for f prime of -3, it's the same as g of -3. And this is the graph of g, so it just wants the function value. And I read from the graph that g of -3 is -1. My answer here is simply equal to -1. In part C, I'm asked for f double prime of -1. I'm going to start at this derivative I found up here, this f prime equals g relationship. I'm going to do one more derivative. So if I do the derivative of f prime, that's f double prime, and the derivative of g is g prime, and it gives me a new relationship. And this tells me that f double prime of x equals g prime of x. If I'm looking for f double prime of -1, using that relationship, it tells me it's just the same thing as g prime of -1. What I'm given to work with is the graph of g. If I want g prime of -1, that just means the slope. So on the graph of g, at the point where x equals -1, I just need to calculate the slope, and I just do a rise over run to track my movements from one point to the other. It looks like I go up 1, to the right 3, so this is going to have a slope of 1/3. So f double prime of -1 is 1/3. The next set of questions are going to take us back to that graph analysis unit that we did in Unit 4. In Part D, the question wants to know, where is f increasing? So if you just go back to that fun chart knowledge, I can see that f is increasing where f prime is positive. But you have to be careful because this is the graph of g. But what I established earlier is that f prime equals g. So even though this is labeled as the graph of g, this is really f prime in disguise. So I'm really looking at that f prime graph. And I see that f prime, this graph, is positive where this is above the x-axis, which is on the interval from 0 to 3. So f is increasing on the interval from 0 to 3 because f prime equals g is positive. It's important for you to make this connection between my graph that I'm asked about, which is f, and the graph that I'm given, which is g. So the statement I've highlighted here is pretty important. I had set it up here, which would actually be okay, but it's nice to say it within the problem. If I want to know where f is decreasing, well, I know that f decreases where my f prime is negative, and my f prime graph, which is what I'm looking at here, is negative on that red interval from -3 to 0 because my f prime is below the x-axis. This is exactly what we had done before. The only new part is making that connection between f prime and g. In Part E, I'm asked where f has a critical point, and we know that a critical point is where the derivative equals 0 or is undefined. Since I've already established that this is the f prime graph, I'm looking for where this graph equals 0, which is in two places, the 0 and the 2. And then I have to classify as a max, a min, or neither. I know that a max is going to happen where my f prime goes positive to negative. I can see that here. And I know a min is going to happen where my f prime goes negative to positive. When I analyze these points that I've identified as my critical points, I see at 0, my f prime goes negative to positive. So that's going to make x equals 0 a min. And I can see that at x equals 2, because my f prime stays positive, that I have neither because I don't undergo a sign change at x equals 2. So x equals 0 and 2 are both critical points because f prime equals 0. X equals 0 is a min because f prime goes negative to positive. X equals 2 is neither one because f prime does not undergo a sign change. In question F, I'm asked about the concavity, if f is concave up or concave down. And again, I'm going to use the fun chart to just help organize what I'm doing here. So f is concave up. So f is concave up where f prime is increasing. I've already established early on that this, even though it's labeled as the graph of G, this is really f prime. So I'm looking where this graph is increasing. So f is concave up on the interval from -3 to 1, is this first one, from 2 to 3. Because f prime equals g, there's that connection connecting my f prime and my g with the graph that's given to me is increasing. The next part wants to know where f is concave down. So f, my concave down is this one, where f prime is decreasing, which is this one interval that goes from 1 to 2. So f is concave down on my interval from 1 to 2 because f prime equals g is decreasing. And again, I made this connection and I wrote it explicitly that f prime equals g. Really, all you have to do is say it once for any given problem. I said it multiple times just to be safe, but one time is actually okay. In my last part here, I'm asked where f has a point of inflection. Using the fun chart, the point of inflection happens in between this column right here. It's when f goes from concave up to down, where f prime goes increase to decrease or vice versa. Since I'm looking at the f prime graph, I'm going to use this line right here. So I'm looking for where f prime goes increase to decrease or vice versa. So when I look at this, I'm increasing, increasing, increasing until I get to x equals 1. And once I hit x equals 1, this goes on the decrease until I get to 2. And then I'm increasing again. So I have 2 points of inflection. One of them is at the 1 and one of them is at the 2. So I just write that as my answer. F has a point of inflection at my two values, x equals 1 and 2, because f prime equals g. There's that connection yet again. Goes from an increase to a decrease or vice versa. So this graph analysis stuff is going to come back at you. It's imperative that you make this connection between the given graph and the graph that you're being asked about. So I'm given the graph of G, yet these questions are asking me about F. So you need to make that connection between the two at some point on your paper. So have fun with this. It's actually just one little step further than what we did with the graph analysis and our fun chart previously.